A, or the top line on your handheld, on your gauge. That's going to be copied directly over along with the fan pressure and the range. So in this case, on our 10 Pascal point, we actually recorded 9.9 Pascal on the gauge. With the bias pressure added in, we have 11.1 Pascal of actual pressure in the enclosure. At this test point, our test fan was on range A. This drop down can be selected or can be clicked, and the range can be changed. So we were on range A. The fan pressure, the second line on the gauge, was showing 89 Pascal. 89 Pascal at 9.9 Pascal of enclosure pressure is going to give us a calculated flow rate. The same thing occurs for 50.1. So this was our 50 Pascal target. The actual pressure recorded on channel A at the point of entering the data was 50.1 Pascal. This was done on the open range, and the fan pressure on open was 255 Pascal. You'll notice that this is split between two lines. You can add lines by clicking the plus button. It'll give you a new line, and you can change the range and enter the fan pressure. So in this case, we split up the 10 and the 50 Pascal between two lines. You want to make sure you leave a blank spot. If you have to add a second line, you do not want to put anything in the blank cell. The depressurization set is going to be very similar to the pressurization set. The biggest difference is the fan is turned around and our channel A is a negative value instead of a positive. Negative channel A with operator location inside is going to be a depressurization test direction. Again, this is automatically set. We're using the same ranges for depressurization. So in this case, we're using A and open to get the negative 10 and negative 50 Pascal points. One thing to pay attention to in this section is the leakage exponent N. This is the slope of the line when you plot your two pressure points on a graph for each set. The leakage exponent should be between 0.5 and 1 to indicate realistic data. If it is under 0.5 or over 1, that usually means that either the wrong range was selected or there's some kind of issue with one or more data points. I'll also show you the opening area calculated based on the two pressure points. The calculate button here, it's a good idea to click this if you make any changes to the inputs, just to make sure you're calculating with the latest data. Below, here's the average results section for these two sets. So we can see the combined equivalent leakage area at 10 Pascal, which this is just the if you added up all the openings into one opening for the enclosure, it would equal a whole 750 square inches in area. That's referenced at 10 Pascal because that is as close as possible to actual opening area. This would be the enclosure leakage as measured. We can see below it's listing the maximum allowed leakage at 10 Pascal that'll maintain a 10-minute hold time. So this would be your upper bound of leakage. If it exceeds this number, your hold time would be under 10 minutes and the test would fail. This is going to show the leakage split. So by default, you're going to have a 0.5 lower leakage fraction. So by default, the software is going to take any leakage measured, split it evenly, and assume that half is in the upper part of the enclosure, half is in the lower part of the enclosure. If you actually have more leakage in the upper portion, you can run a BCLA test, which we will get into in the next level. Below that, we have the averaged exponent value. So the average of the two sets is 0.7 in this case. And to the right of that, we have our hold time statement. So calculated hold time using descending interface as the calculation method. We're getting 10.3 minutes. This is resulting in a pass. If we expand this detailed results section, we can actually see the other hold time results as well. So descending interface would be the top one. That's just a repeated result. Continuous mixing would be the other option if the agent and air is mixed continuously and forms a concentration. The hold time would be 9.1 minutes. That's 9.1 minutes to go from the initial or the starting concentration to the minimum. Below that, it's showing the minimum required extended discharge rate. This is for extended discharge hold times, which we'll get into more in upcoming sections. Basically, it's showing the pounds per minute of agent that have to be put back into the enclosure to make up for any agent that's lost from leakage. The next section is going to be venting and peak pressure analysis. For this specific example, we don't really have an issue with peak pressures. We are testing with a halocarbon agent, so we can expect both a positive and a negative peak pressure. The minimum leakage required to relieve the negative peak pressure, which should be the highest value, is 489 square inches. As you can see, the enclosure area used for pressure relief is going to be 1,313 square inches. These are both being referenced at 125 Pascal, which is where vents are going to operate. So the minimum leakage required to relieve peak pressure is being met by the enclosure leakage. So even though we do not have a pressure relief vent, none is needed. As you can see, our positive peak is going to be 3 Pascal, negative peak is going to be 0. Had our enclosure leakage been a lot lower, or maybe if we had more agent in the enclosure, we could see some higher peak pressures. A vent is not needed in this case, although just to demonstrate quickly, we'll add one in. There's a drop down where you can tell what type of vent is being installed in the enclosure. We'll say gravity, positive and negative, so it would open both directions. Discharge time is just going to be the time it takes for the agent to be dispensed in the enclosure. 10 seconds is common for halocarbons. 60 seconds would be the normal time for inert agents. So if we're using a halocarbon, we'll leave that at 10 seconds. The enclosure pressure limit, that's just the maximum pressure the enclosure can withstand without damage. 500 pascals is the default. This can be changed if you have data to prove that the enclosure could withstand more. And it's going to be based off the weakest point of the enclosure. So 500 pascals is a pretty safe limit for almost any enclosure. A lot of enclosures can take up to 1,000, but ideally you would have some kind of... On the right, it's stating that we're using the FSSA equation to calculate vent area. We'd recommend leaving this as FSSA. It tends to be the most realistic peak pressure calculations. The venting section, there are 2 drop downs here. It's asking for the vent that we're specifying, are we giving data for the enclosure and the vent combined, or are we specifying for the vent only? Typically, you want to leave these on enclosure and vent. When you put a vent into an enclosure, a peak pressure or pressure relief vent, you would want to test it in its installed condition. So ideally, the enclosure is going to be pressurized to 125 Pascal. The position of that vent will be marked, and it'll be propped open in that position. And then you would run another door fan test to 10 and 50, and negative 10 and negative 50. The new data is going to be used by the software to determine how much vent area you've added. And then assuming a vent is needed, that may relieve the peak pressures being generated.